All right, I think we're going to start. Thank you very much for coming. So the title of this talk is How Do Fibers Work? A Peek Under the Hood, even though I quite like the provisional title in the schedule that just goes Fibers. So as you're going to be quite different from what I normally do. Generally, I take a concept or an abstraction and then show you progressive code examples, treating the implementation of that thing pretty much the black box, which is great. It means that we've developed a strong abstraction if we can do that. But even though I love abstractions and what they allow us to do, I still think that for many engineers, like how does this work is a very fun question to answer. So I hope you're going to enjoy this journey into the runtime system and that powers Cat's effect and FS2. So who am I? My name is Fabio. I'm a principal engineer at Energy in London. We do lots of Scala and FE, so if you like that, we're hiring. Come talk to me. And I'm also an open source developer, a system founder, mostly as a core maintainer and contributor of FS2 and Cat's effect. But let's get straight into the code. And what I like to start is some very high level code of what we can achieve with this model. So this is a minimal, but nonetheless fully functional TCP server. This is FS2. It's not important to understand every single line of it, but I'm going to give you a quick overview. So we call server there, and server represents a TCP server. And the way we represent it is by a stream of connections. So what happens is that the stream is going to emit a new connection every time we receive one. And it's a stream of sockets, and they are resources because we can close them. And so we need to lift this resource into stream by a resource, and this ensures that the socket is going to be closed once we're done with it. And then we flag map on that, we have access on the socket, and we describe the process of interacting with this socket also as a stream. So what I'm doing here, I'm generating numbers from 0 to 10, and then transforming them into strings with a ping message. And that metered method means that they are emitted once per second. So basically I'm emitting numbers from 0 to 10, 1 a second. And then I'm just going to encode them in binary and then send them to the socket. That's the socket writes. And finally, I'm saying that whatever happens, I want to send this end of output to the socket. So I'm adding some finalization logic there. And the pi join unbounded there means that I want all these things to happen concurrently. So obviously, you don't want to start serving a connection only after you're done with the previous one. You want to do all of these things concurrently. That's what pi join unbounded does. And finally, interrupt after 10 minutes. It's kind of self-explanatory. But what it does is going to stop this server after 10 minutes, and it's going to do so gracefully. So it's going to wait for all the finalizers to run, for all the end of sockets to be sent, and then it's going to shut this down. And this is also compositional. So this is not going to actually shut it down the app. It's just shutting down the server. I can just say ++ another stream and keep going with something else. So the interesting about this model, it's very high level. It gives you sort of quite a few capabilities. We've seen resource safety, we've seen concurrency, we've seen interruptions. But there's also another thing that's interesting about it, and that it runs on a fixed number of threads, of JVM threads, which seems weird because obviously we're getting way more connections than threads, and also we're doing a lot of sleeping, but yet somehow it runs on a fixed number of threads. So it's fully non-blocking. So what I'm interested in this talk is to actually find out how is this possible. What does it mean, first of all, to be non-blocking, and how do we achieve that? So let's start with kind of defining what are the layers of abstractions that you're seeing here. So the first one is FS2. And FS2 gives you this very declarative, high-level, and also safe concurrency model. So it offers many combinators. We've seen a couple. We've seen metered, we've seen pi join unbounded, interrupt after. But also, it has this underlying concept of lifetime. So you can think of a stream emitting as the lifetime of this concurrent resource. And this means that the model is inherently safer than what you get with just I/O because of this lifetime concept. So then, one layer down, you get the Cat's effect type classes like concurrent or timer. They were in the signature. And this is a specification for low-level foundational primitives. So with FS2, we build this high-level model based on a spec for these foundational low-level primitives. And finally, a concrete type like Cat's effect IO will give you concrete implementation of the runtime system that implements those primitives. So just to make it clear, as a user, I highly recommend using a high-level model like FS2. It's way safer and way more declarative than what we're going to see today. Because today we're actually implementers. So we are people implementing Cat's effect, and we're just going to look at the low-level runtime that powers I/O. So how does those primitives work under the hood? Okay, so this is like a little story in chapters. So the first chapter is actually understanding asynchrony and concurrency. So these are like very broad terms. So I actually want to give you a nice semantic model for what these things are and how they work, and this is going to help us a lot when we actually go to the code. So I'm going to use a bunch of words in this section, like thread and process, and in this section, I mean them in a very loose way. So I'm not talking about operating system threads, I'm just describing general concepts. Okay, so first of all, what's an asynchronous process? A traditional definition for an asynchronous process is a process that executes outside of the program main flow. That's a fine definition, but I'd like to change it a little bit for reasons that will become apparent fairly soon. And I want to say that an asynchronous process is a process that continues its execution in a different place or time than the one it started in. So it's still fairly vague, so let's have a look at a picture. So you have this process. It executes 3 steps, and then there's an async boundary, and then it executes the other 3 steps somewhere else. So what's an async boundary? It's just a very general concept. You can think, for example, as a computation that executes some steps, and then is moved to another node in the network, and then it does the rest of the steps in that node. So that's an asynchronous boundary. It's like resuming somewhere else. Or you can think of scheduling to another operating system thread. Or you can even think about it gets put at the back of the queue and then executes later, like with JavaScript and event loops. It's just a very general idea of kind of ending in one place and resuming somewhere else. And what's concurrency? So naively, concurrency means that multiple processes are executing at the same time. But this definition is just way too wide. It's like so generic that it's actually of little use. And in fact, it also overlaps with parallelism. So we want something a bit more specific. So I'm going to say that concurrency is a program structuring technique in which there are multiple logical threads of control whose effects are interleaved. So first of all, it's concurrency about structuring programs. It's how your program looks like, not necessarily how it executes. And there's this idea of having multiple logical threads of control, which gives us modularity. You know, we can have one logical thread that does one thing, another logical thread that does another thing, and it's modular. And because they are interleaved, you see, the effects of those logical threads being interleaved, which gives you like the idea of, executing at the same time. So let's define a logical thread then. It's a very simple definition. So a logical thread is just a sequence of discrete steps. However, even though this might seem quite trivial, it's important to define that the steps are discrete, because once you have a discrete step, you can think about the concept of interleaving. It's going to look like that. We have 3 logical threads, A, B, and C. And those steps are interleaved. So you get A1, B1, B2, C1, A2, A3. So they all interleave together. And because I have discrete steps, I can say I'm going to do one step of logical thread 1, one step of logical thread 2, and so on. And the process of interleaving those logical threads is called scheduling. And for now, just think of it as like a magical thing. It just happens that they are interleaved this way. So in this picture, I'm showing like 3 logical threads being interleaved into one, but actually that's not necessarily the case. You could interleave 3 logical threads into 2 logical threads at a layer below. And it works kind of very similarly. You have, A1, B1, and B2 on A prime, and C1, A2, A3 on B prime. And there's a couple of things to be said about this. So first of all, don't assume that just because we have the layer below, now that's it. We could have layers on top of layers. You just keep on interleaving. But the key thing is, generally, the more you go up this tower, the more logical threads you have. So you don't want to interleave one logical thread at level 1 into 2 at level 2. You want to say, I have 10 logical threads at level 1, and I'm going to have 3 at level 2, and I might have 1 at level 3. And so you can see there's this notion, and this is called M2N threading. So we sort of map M logical threads at a higher level into N logical threads at a lower level, where N is way smaller than M, typically. And as you can see, this kind of gives rise to the notion of this sort of tower of threading. So it's a pretty sort of not very good picture because I hit the limit of my ASCII fantasy. But the sort of the top of the picture here is the like many threads at the higher level, and then they get interleaved into slightly fewer threads on the lower level, and then again slightly fewer logical threads at a lower. They're still below that. And then the question might be, okay, when does this tower end then? Is it like just an infinite tower? And we'll have a look at that in the next chapter of what does it mean to get at the bottom of the tower. So but the key idea of this section is that threads are abstractions. And in particular, a logical thread gives you a synchronous interface over an asynchronous process. And again, this is best explained in pictures. So let's say you have, this is our definition of async process. You know, it executes some steps, then there's an async boundary, and then it resumes somewhere else. And then let's have a look at those interleaved threads. So if you just focus on A for one minute, if we have a look at the top layer, where we are in the threading layer, it's synchronous. You know, you have A1, A2, A3, A4, A5, one after the other as a sequence of discrete steps. But if you look one layer below, when they're getting interleaved, there's actually asynchrony there, because you see A1 does one execution, one step of its execution here, and then it resumes somewhere else. So this duality between layers is kind of key to understanding how this works. Depending on where you are, there's kind of like a relative view. If you are within the thread, it looks synchronous to you. But if you are the level below, where threads are getting scheduled, then it's definitely asynchronous. And although it's sort of clear to see when there are like two logical threads at the layer below, it's also true when there's only one. Like if you look at this picture, A1 is still asynchronous because it starts here, and then it's going to resume at a later time here, and there's something else happening in between. So for the purposes of this layer, the A logical thread is asynchronous, but for the purpose of this layer, it's synchronous. And for us, that's great, because we like synchronous abstractions. They're just a lot easier to reason about, because we have a notion of, just do things in sequence, one after the other. So, but then, what does it mean to block on this semantical model that we're trying to explore? What does it mean to actually be blocked? So the key concept is that blocking at one level always means suspending at the layer below. So let's say you have like two logical threads, A and B, and A executes A1, and A1 sort of wants to block until B2 is executed, and then once B2 is done, it wants to keep going. Again, sort of synchronous interface at the top layer, we're just waiting, so it seems like we're blocked. But if you look below at what the interleaved bottom logical thread is doing, so A1 executes for a bit, and then just sort of suspends its execution, so sort of gets queued or goes somewhere else, and then gives the possibility for other steps to be run, and then at some point B2 is going to run, and then B2 just schedules A1 back. So, it schedules A2 back. So again, what we think of blocking is actually just, again, asynchrony. We just don't see it because we're at a layer where we don't see the interleaving. We just see the synchronous step. And then we'll see how this maps into actual threads and why some blocking is good and some blocking is not that good. But at least as an abstraction, blocking seems good. It's a very intuitive way of thinking about conditions being fulfilled. I just wait until the condition I want happens, and then I keep going. So, quick recap of this section. So, async processes resume somewhere else after an async boundary. And logical threads abstract async processes as synchronous sequences of discrete steps. So, very simple abstraction. And then multiple logical threads can be interleaved to achieve concurrency. And finally, blocking means suspending one layer down. And critically, logical threads at that layer keep running. So if I blocked a layer 1, layer 2 is still free to do other things, because what happens is just that it's not scheduling layer thread A and layer 1, but it's scheduling other things. And that's it. That's our model for concurrency and asynchrony. And this model is going to help us throughout the talk. So especially this sort of duality between synchronous at one layer versus asynchronous the layer below. So, but how do we map this to real-world concurrency? So, how does this concept map into, you know, the JVM and the OS and the real world that we have to deal with? So, first of all, I want to mention the distinction between concurrency and parallelism. So, concurrency is like interleaving these discrete steps, and parallelism is actually running these discrete steps at the same time. So, if you think about the tower, we interleave at some point with the bottom layer, which is actually the number of processors. And at that point, we might actually run some in parallel, depending on the number of processors. But the key idea here is that those things are actually independent. It doesn't matter. For the, you know, you can have concurrency and only run on one thread. You just keep interleaving. And you could have parallelism without concurrency. You just map, you know, deterministically to each processor. And you can have both. And what we normally have is both. You have a lot of interleaving, and then all the way down, there is some parallelism also happening. And for this talk, we're just going to treat parallelism as an implementation detail. We don't care how do we map to actual processor. We just care about this process of interleaving, because this is what, you know, most things end up needing, especially if you deal with events happening. It's not so much about running at the same time, but rather dealing with lots of things at once, events and reading from files and doing other things. And then I mentioned this concept of like this tower of end-to-end threading, and there are layers. So what are the actual layers that we actually deal with? So the first layer is actually OS processes. And now by process, I mean like the specific term in operating systems. And those are end-to-end processors. And they have their own execution state in the operating system and their own memory space. So they're quite heavyweight, because every time you switch, you need to change execution state, and you need to change the memory space as well. Then you have OS threads, and these are end-to-end with processes. So you can have multiple threads running on one process, and they still have their own execution state, but they share the same memory space. So they're a bit more lightweight than the processes. And crucially, right now, JVM threads are the same as OS threads. This wasn't the case quite a few years ago, and it might not be the case when, you know, Fibers and Project Loom arrives, but for now, JVM threads are just the same as OS threads. And then finally, you have Fibers. Again, they are end-to-end with threads, so we're going up one layer. You can have many Fibers running on one thread, and typically you have a lot of Fibers running on a very few threads. And they just share everything. Like the OS has no notion of scheduling those things. They just share in user space. So same execution state and shared memory space as well. So let's talk about blocking then, because as I said, like blocking on one layer just means suspending at the layer below, but not all layers are created the same in real world concurrency, because they have different levels of how heavyweight it is to switch. So the key thing here is that JVM threads are a scarce resource. Because they have their own execution state, you can only have so many of them. And so if you only have so many of them and you suspend one because you're blocking, then you're getting rid of a precious resource of which you only have like a few of. And so blocking a JVM thread is actually not that good. You won't be able to scale out if you want to operate as nice synchronous one thread per request model. And yeah, so when most people say this thing is blocking, what they mean is it blocks the thread. So from now on, by blocking, we're going to mean blocks the actual JVM thread. But depending on what level you're in, not all blocking it's bad, right? So fibers aren't scarce. We see that fibers are actually very lightweight because the OS doesn't have to create this huge context for them. And because they aren't scarce, and because blocking a fiber does not block the underlying thread, right? You just suspend the fiber and the thread does other things, then blocking a fiber is perfectly fine. And we call this kind of blocking semantic blocking or asynchronous blocking. But we just mean that we're blocking a fiber and not a JVM thread. And this is pervasive. We're going to see that a lot of things in the ecosystems, like sleep, like defer.get, like fs2q, like fiber.join, they do semantic blocking. So because blocking is nice as an abstraction, we just don't want the cost. And this is very low cost because, again, one layer below, we're just suspending and the thread does other things. And finally, I want to talk a bit about scheduling. So in the previous section, we were looking at scheduling and this sort of magical process that just happens. But in reality, obviously, it doesn't happen by magic. There are a few mechanisms. And the two main families are cooperative and preemptive scheduling. So preemptive means that the scheduler is in full control of which threads or fibers are running at any given time. So he's going to run a few operations on one and then stop it and then run a few operations on the other one and so on. In a cooperative model, instead, so the tasks themselves, they suspend themselves. So they're going to say, I want to run now. And then after a while, they say, OK, now I want to yield back. So they sort of cooperate with each other to achieve interleaving as opposed as having the scheduler being in full control. And actually, I think that when we say, oh, cats affect as fibers, most people that are familiar with concurrency, they instinctively think of something like this. They think there are a bunch of, these are fibers, and then there is an I/O runtime, which all the fibers share, and inside the runtime there's a scheduler that we've written that kind of does the interleaving. But it turns out this is not a great idea. So there are a few issues. First of all, you need to write the scheduler. So that's the complexity of writing the scheduler itself. And this sort of scheduler is better suited for preemption because you're in full control of which fiber is running at any given time. But also, this is makes it harder to do end-to-end. Because let's say you decided the full order of these fibers in your scheduler, then you have this order, and if you want to run on one JVM thread, that's nice. You decided the order, you just run on the thread sequentially on your order, that's fine. But if you want to do end-to-end, now not only you need to figure out the order for the fibers, you also need to figure out how to map that into the underlying threads. So it gets sort of quite complicated. So the way things work instead is via a cooperative model. So things look a bit more like this. So these are fibers, or IOs. And each of them has an interpreter, which we call the run loop, and we're going to see why it's called the run loop. And the run loop submit itself to the scheduler. And as it turns out, we already have a concept of scheduler on the JVM. It's just a thread pool, right? A thread pool wraps a certain amount of threads and then allows you to execute tasks. So what the fiber can say, I want to submit myself, that's a bit of a task. And then after a while, it's going to say, well, I want to submit myself again, and that's kind of yields back control to thread pool, which is then free to run other fibers. So they all cooperate by sort of submitting and yielding back, with each other. You get the end-to-end mapping for free, because the thread pool already takes care of mapping things to a certain number of JVM threads. And you also don't need to write a scheduling algorithm. You just need to be careful with how often you yield back within your fiber. And when you have this end-to-end cooperative scheduling, that's it. That's what fibers are. So it's different from threads in a few ways, and this is one of them. The architecture looks more like this. You have independent interpreters that all submit themselves and yield back themselves to a thread pool, which is our scheduler. Okay. And as it turns out, in terms of code, we already have some building blocks. So execution context in Scala, it takes a runnable and returns unit, and that's just a signals. It just represents the concept of submitting something to a thread pool. So we have this bit, and that's execution context, the thread pool here below. And we also have a schedule executed service. Now, for some reason, Scala doesn't have a schedule execution context. I think it's a mistake. It really should. So you have to go to the Java API. But basically, it's very similar to an execution context, except you can also say, I want to schedule this for a given time. So it's going to wait a bit and then schedule it. And this signature here, they're from Java. They're slightly adapted. So there are some minor lies there to make it a bit simpler. But this is the gist of it. So we're going to see later that we have these two building blocks to start building our fibers. OK. So we're kind of done with the sort of semantic model of concurrency. We're now going to start getting into the nitty-gritty of how does I/O look like. So what's an I/O? An I/O is an I/O of A. It's a computation, the description of a computation, which can produce one value or fail or never terminate. These are the three things that an I/O can do. And it's referentially transparent, just pure. This is usually important for compositionality, but I've talked about this a lot in my other talks. So for now, we're just going to assume that you already buying into this. And he has many algebras. So it's monad, it's concurrent, and so on. But today, I want to kind of divide the API in 3 branches, in 3 families of functions. So the first one is what I like to call the FFI, so foreign function interface. What I mean by this is like it wraps side effects into I/O. So if you look at purely functional Scala as a subset of Scala, which has no side effects, so no expressions which aren't referentially transparent, the FFI takes impure expressions and puts them into I/O. So it's kind of our interoperability layer with normal Scala. So this is how you build your primitives, like you want to wrap, print line or whatever. And then we have the combinators. So combinators allow you to build complex I/Os by just composing smaller ones. And in a pure application, like 90% of the things you do is in combinator land. There's the payback that you get to build your programs this way. And then finally, at the end of the world, you have your runners. So you're done composing these I/Os. You have now this giant I/O that describes your flow. And then you translate your I/O to side effects at the end of the world. And if you have something else like stream, is the same. Stream translates back to I/O, and then I/O will translate back to side effects. At the end of the world, though. Don't do it, not there, because otherwise you lose purity, and that is no point. Or at least there is less of a point. And so let's hear some examples with the real I/O. So for the FFI, I think the most common function is delay. It takes like a synchronous block with side effects that produces an A and gives you back an I/O of A. So in the I/O of CatFFI, this is called apply on I/O and delay in the type class. But basically, this is your basic building block, right? If you want to say print line something, you're going to say I/O I/O delay print line or I/O applied or print line. And that's your sort of primitive I/O that wraps that side effect. And then you have these async things, and the main thing about those is that they look weird. So since they look weird, but the name is kind of enticing. We've been talking about asynchrony, and they kind of seem relevant. So they have their own section. But yeah, we're going to come back to why they look so weird. And then you have combinators. So this is the nice stuff. So you have ways to compose your I/Os sequentially. So pure map, flat map, and all the derived stuff, like and then and as and void and all of them. You have things for error handling. You have here I just put handle error with and raise error, which are like the moral equivalent of try and catch. But these are from monad error, and there's like a lot more of these. There's like attempt, recover. There's a million. And then you have the concurrent ones. So you have start, which is your basic forking primitive for fibers. It just starts on I/O in its own fiber. You have race that kind of raises to I/O concurrently. Sleep to do asynchronous non-blocking sleep, timeouts, and so on. And you have resource safety, guarantee, brackets, and whatever. And this is the nice stuff, as I said. And so you use these combinators to build from your primitives until you reach like the big I/O that represents your old program. And then at the end, you're going to have your runners. Now, the main runner is actually just saying that I/O is the main I/O. So you extend I/O app and just say, well, my run I/O, the main I/O is this one. So you actually don't need to be aware of how things work internally. You just need to say, just like in normal Scala, you say main equals something. In purely functional Scala, you say the main equals an I/O, which is your main I/O. But then you have your unsafe run async, which runs an I/O asynchronously, and it's the general form. And we'll see why it takes that callback there. And then you have the unsafe run sync, which only works on the JVM. And if we have time, we'll also explain why that's the case. But so I want to show you actually how do you go about implementing such an I/O. And to do that, we're going to look at the simplest I/O that you can possibly imagine. So the bare minimum is going to be pure. That's like sort of the minimum requirement. It's going to have a synchronous FFI, so you can wrap things like print line. It's going to support sequential composition, so basically monad. Do this I/O, take the result, and compose it with another I/O. It's not going to do any error handling, so exceptions are suspended, but then when you run, you cannot do anything with them. You cannot say handle error, so they're just going to bubble up. There's no asynchrony, no concurrency. It's not stack safe. It's not resource safe. It's just very, very simple. But so if we look at the API for the simple I/O in those terms, you have your FFI. It's just delay. Takes a synchronous block of side effectful code and gives you an I/O of A. It's a monad, so it's got pure flat map, and from those we can derive map and void and all the other things. And then you can run it with unsafe run sync. And since it does not have any asynchrony, it's fine. We can always run it synchronously at the end of the world and just get side effects and an A back. So some of you might have noticed that this very simple I/O is actually isomorphic to this. So it's just a function from like unit to A. And in fact, you can implement it just as a function as unit to A. So that unit thing, that's the suspension, which means that you get your side effects are suspended, and then you can just flat map over that. But we're going to look at a different implementation, because if you have this sort of direct encoding, it ends up to not really scale well with complexity. When we add features like stack safety or error handling or concurrency, we end up sort of getting lost in this sea of complexity. We want something a bit more modular that lets us add features and think about them in a better way. So the technique we're going to use is sort of the interpreter pattern, kind of the FP universal pattern. We just create a data type describing what we want to do. And then most operations just get translated into that data type. And then we just need to figure out how to interpret the data type into effects, side effects at the end of the world. And for the interpreter itself, we're going to use sort of this technique with a run loop and a call stack. And I'm not expecting anyone to be familiar with other terms, but we're going to see like what they mean and why we do it this way. So let's look at our data type first. We just need, synchronous FFI and monad. So we just need 3 cases of our data type. The first one is flat map. And if you know, like monad, this should be very familiar to you. It just takes an I/O and a function from the result of the I/O to another I/O. So it's just the signature of flat map, pretty much, as a data type. And then you have pure, same thing. It just takes a value with no side effects and gives you back an I/O. And then delay. And delay needs to use this sort of function from unit to A to allow us to suspend the side effects and execute them only when we want them. And that's kind of gives us the purity. And so let's have a look at a simple program in I/O and see how it gets translated. So you have your primitives, and we're going to use read, and they just sort of suspend Scala I/O read line. So if you call it apply, it's going to basically build a delay node. And then put, sort of very similar, but it suspends print line instead. And then we have this little program called prompt that says, I'm going to put the string, what's your name? And that little operator there just means flat map and ignore the result. So in this case, it means and then. So I'm going to print what's your name and then read from the console. And then you have another program called hello, which is I'm going to flat map on prompt, get the name from the user, and print it out. So it's very simple. And all this does is actually build a data structure. And the data structure sort of looks like this. So you have a flat map node, which is the latest one, yeah. And then you can see that the continuation there is just a delay with the print line of the name. And then inside that you have another flat map, and you have the 2 sort of delays, one that prints the name and one that reads from standard input. So that's our data type. Now we need to go and interpret it. So run loop. This is how we're going to write our interpreter. So what's a run loop? So it's very simple. It's just kind of a recursive function that executes instructions one at a time. So you can look at each of the nodes of that I/O as an instruction, and the run loop is just going to kind of go through it and execute it one at a time. And it keeps track of some state. And the state is the current I/O and the stack of binds. So the stack of all the flat maps. Because in a way, the flat map represents the next step. So we're going to put them in a stack, similarly to how sort of real side effecting code there's a stack of function calls. We will have a stack of this, A to I/O of B. And the way it looks like is like this. So you have your current I/O, which is an I/O of any, and then you have the call stack, which is a stack of any to I/O of any. Now you might be surprised to see any there, like in functional code. It's weird. But the reason is, so the tree that I/O builds is a type tree, right? So one function might be into I/O of string, and another one might be string to I/O boolean, and so on. So it's hard to keep the types in a simple data structure. But because we know that the tree is typed, we can use an untyped representation internally and then just convert it back. And the user has no way to build like a unsound I/O, and we just get to use a very simple data structure like a stack. And so yeah, so any lets us use a very simple data structure over this sort of type tree. Okay, that's it. So that's how actually it works. So just bear in mind the type of flat map there. You have a current I/O, which is f of a, and then you have the rest of your I/O, which is a function from the result of f of a to the next I/O. And our unsafe for async just as this loop, which takes the current, which is I/O of any, and the stack. And at the end, we're going to run it by just saying loop I/O with an empty stack. And so let's see. So let's say we hit a flat map node. So we know that there is a current I/O and something that we need to do once we have the result. So what we're going to do, we're going to push that continuation on our stack because we cannot evaluate it yet. We need to first evaluate the current I/O. So what he's going to do, he's just going to take this f and put it on the stack for later. And then he's going to recurse by passing this fa here. See, fa, it gets into the loop. So we just postponed the continuation for later by putting it on the stack, and then we go inside the I/O. And the I/O itself might have other flat maps, and every time we encounter one, we put it on the stack and keep recursing on the inner FOA. And then at some point, we encounter a delay node. And that, if you remember, had like that function from unit to A. So we're just going to evaluate that function, and this is where actually the side effects are happening. And as I told you, this I/O does not do any error handling. So at this point, if there was an exception, we're just going to throw ourselves. There's no error handling. And then, since now we have a result and we already done the side effects, we can rewrite the current I/O to just be pure. So we've done the effects. Now the current I/O becomes pure of the result. And then once we hit the pure, it means we're at the bottom of a flat map chain. And so we try and get the latest continuation from the stack with the stack.pop. And there are two cases. If there's none, it means that we got to the end of a program. We actually got to the final instruction of an I/O. We just need to return A, which we have. It's V here, but it wasn't any, so we need to just cast it back to A. And we know this is going to be safe because the I/O was constructed in a typed fashion. And if it wasn't the end of the I/O, we know that we have, on the stack, we have an A of I/O of B, and we have an A here. That's this V there. So we just need to get the next I/O by just injecting the value to the continuation. So you just take the A and put it into the F, and you get the next I/O. And then you just loop. So it keeps doing this sort of continuously until either there's an exception, or he hits the end, or you wrote a recursive function and never terminates, which were the semantics that we were expecting. So I'm not going to go too much into the details of how this works, but this technique sort of scales well with complexity. We can add more stuff. So I'm not going to explain this, but this is very, I'm going to just glance at it. But this is how you implement error handling. You just add two nodes, one to raise an error and one to handle an error. And because you have an handler, now your stack contains two kind of binds. He has the normal bind, and you also have the error handler, which takes a throwable instead. And then both flat map and handler widget just push their respective handlers on the stack. And delay changes a bit. So now I'm going to try to do the side effect. And if I succeed, I'm going to rewrite the current I/O to be pure. And if I failed, I'm going to write it as a race error. So I'm going to say, if there's an exception, I want to translate that to a fail I/O. And then pure does the same. And race error is quite interesting, because what race error needs to do now is kind of unwind the stack, trying to find an handler for the error that you've just raised. So what it does, just drops from the stack all the binds that were not error handlers. And then once if it cannot find any, it means that you didn't handle the error, just throw it again. And if you did, I'm just going to handle it, which gives you an I/O, and I can keep looping. But the interesting thing here is this stack drop while the things that are not handler. Because if you think about the semantics of error handling, it's short circuiting, right? So you're going to skip over the flat maps until you find an handler. And what we're doing here, we're just dropping the flat maps until we find an handler. So it realizes that sort of semantic sort of rather beautifully, in my opinion. Okay. That's it. This is how it works in a nutshell, and you can go and write your own I/Os. Very simple. But what I want to talk about now is this async thing. So this weird shape, and we're getting there. we see like all these disparate pieces are going to come together, and then we're just going to be able to just implement fibers in a few lines. So async has this very weird type. So the first time I looked at this, I was like, oh my God, this is just like, doesn't make any sense at all. You have either true of A to unit, and so you have this async that takes a function, and the function takes another function, and they all return units, so I don't know what they're doing. So let's try and understand what this thing does. So the first thing to understand that async does not introduce asynchrony on its own. That's the key thing. A lot of people think that async will create an asynchronous I/O out of nowhere. Well, that's not what it does. What async does, it takes something that's already asynchronous and it just wraps it in I/O. So it's just giving you an interface over an asynchronous process. And we'll explain why the type looks that strange. So let's go into there. I want to briefly mention this thing called continuation passive style. So what continuation passive style means is like the idea that instead of returning a result, we just call the rest of the computation with it. So simple example, I have a function to add two numbers, and this is just our normal function. You just return a plus b. And then a function to double a number, again, normal function. We just double it. So if we are to CPS these things, we're now going to pass in a callback or a continuation, which represents the rest of our computation. So add is going to take two integers and also a function from int, which is the result, to unit. And that represents, all the rest of the program until its completion. And it can just return unit now, because it's only going to call this function, and this function returns unit. And what you're going to do, you're going to produce the result, but instead of returning it, you just pass it to the rest of the computation. So you're explicitly saying, so treading along this sort of chain. And then double is the same. It takes an int, and it also takes this idea of the rest of the computation, which is an int to unit, and produces the result and pass it to rest. And finally, we can build sort of normal code by chaining these callbacks together. So you have add 1, 2 takes a function. The function is the sum. We double the sum. It takes a function. The function is going to take the doubled, and then we just print it. And so it then works. But so what has this given us except for like confusion? Because right now I only see confusion, but like no benefit. So as it turns out, if you say that foo as type A, it means that you have to return an A here and now. You can't lie with your types. You're saying, I want to return an A, and so you have to, here and now. But async processes continue somewhere else. So they're like in sort of conceptual conflict. You want to return something now, but you don't know where now is because you're going to resume somewhere else. So what you can do instead, you're going to pass a continuation. So whatever you resume, the resume process is going to call the continuation and keep going. So as it turns out, sorry, async processes are just inherently CPS. So you don't have a foo that returns A, but you have an A to unit to unit. So you have something that takes a callback and is going to resume somewhere else, and is going to call the callback and keep going in this sort of chain of callbacks. And when you take into account errors as well, this is what you can end up with. So all async processes are going to have this shape, or something that can be transformed to this shape. They take a callback, add a trovol of A to unit, and just return unit. And that callback represents the rest of the computation. So once they have a result, which might be in a different node, different thread or whatever, they just call the callback and you keep going. And that's what async does. So async takes one of those async processes and gives you back an I/O. So we're now getting a nice, again, synchronous interface, and this should ring bells, over an async process, because once you have an I/O of A, you can just flat map, which again gives us this illusion of synchronicity. But what's actually happening is that somewhere else, someone is calling a callback with our result. So how do we change the run loop then when we have async nodes? So first of all, we need to change the type. Since our I/Os are now async, the whole run loop becomes async. So the run loop cannot return A anymore. It needs to, in turn, take a callback to kind of keep going with this chain. And then the rest stays the same. You just, you keep the same status, the same state, your current I/O, your stack of continuation, and this callback. And there's a few changes inside the loop when you hit those terminal cases. So before, in a synchronous I/O, at some point we were like throwing an error if we reached the point where there was a raise error node and no handlers. What we're going to do right now instead is just call the callback with left, because we're calling the rest of the computation with the fact that we've like finished with an error, and it might be somewhere else where the error is handled. And similarly, in pure, when we reach the final result, we just return it. What we're going to do now is just call the callback with it. Actually, there's a typo. Should have put right of, the v, because it takes an either. But same, you just call the callback. And so you build this chain of callbacks, and finally you need to kind of finish the chain. And that's why sort of run async, in effect, if you're familiar with it, takes a callback that the user has to provide. But the final callback is often just a reporter. Just says, if there's an error that wasn't handled, print it out. And that's it. And so, how do we deal with the async node in the run loop? So just a reminder, that's how the async node look like. It takes this asynchronous process, which takes the rest of the continuation and makes it resume somewhere else. So we're actually not doing anything. The K already has all the magic to do it the asynchrony. We're just wrapping. So once we hit an async process, the first thing we need to do is kind of compute this rest of the computation. And it's going to be a function. It's going to take a result, either true of any in this case. And then I'm going to say, depending on whether that result was a left or a right, I'm going to rewrite things as a raise error or a pure. So quite similar to what we were doing before in the synchronous case. And then what does it mean to sort of encode the rest of the computation? Well, since the computation is just a loop over this stack, the rest, it just means just loop with whatever stack is left. Thank you so much. Yeah, I was dying there, so thank you very much. Since we refine this computation as just a stack, which we are looping over, the rest of the computation just means loop over the rest of the stack. And once we have that, we have this async process, and all it needs is just this, what the rest of the computation is, and we just pass it into the function. And when we do that, we just send in the rest somewhere else using the async process, which we don't even know what it is. We just know that it's going to end up somewhere else, and so we're going to send the rest of the computation somewhere else. So it's kind of mind-bendingly simple, because it's just functions, calling functions. But the key idea is that the magic is not in the async node. The magic is in K. So K itself is going to be something, and we're going to see very soon what it is, what family of things look that way, which already knows how to do asynchrony. All we need to do is kind of propagate the call stack. And because we propagate the call stack, and the call stack is flat maps, we actually get in this synchronous interface, because we have all these four comprehensions, which look synchronous, but they're getting split over multiple sort of async boundaries. So as it turns out, that's pretty much it. So we now have all the ingredients to build our fibers. So please bask in the glory of this picture. So you have your conceptual picture of fibers. And if you remember, I said that a logical thread is this sequence of discrete steps. And now we do have something that represents that sequence. That's a stack of continuation, right? Each bind is a discrete step. And then each of these get interpreted by a run loop. We've just seen what the run loop does. And then we know that every now and then, it needs to submit or yield back to a scheduler. But we do have a scheduler, execution context, which has a submit, which, by the way, fits that async shape. But because we want to link A1 with A2, each submission is going to be async. So we literally, if you look at this picture, it literally is the visualization of the idea of putting some of the call stack somewhere else, which is exactly what that async node was doing. So believe it or not, that's it. That's fibers. So once you have async and you have a way of accessing a thread pool, you can now build this cooperative system of logical threads, which look synchronous here, because remember, these are just flat maps, but end up being asynchronous here, and they kind of yield to each other cooperatively by calling async of submit every now and then. So the runtime system then just needs access to two things. It needs an execution context for doing this forking and yielding, these submissions, and it also needs a schedule executor service to do the sleeping. And if you've ever wondered why IO app has those weird context shift and timer, that's what they are. So context shift is an execution context for forking, and timer is a schedule executor service for sleeping. And then your main is just basically the run loop. So how do we do the yield then? It's so like mind-numbingly simple that it's like so weird to understand. But basically what I'm saying, I'm using async here, right? And async takes a callback. So the thing you need to keep in mind is that callback represents the rest of the run loop, because that's what we pass in the interpreter. So when you see callback, you just think rest of the IO. And then I'm just going to execute, so submit to the thread pool, the rest of the IO, and I'm going to pass to that unit, which is just a simple thing that it needs to resume. It has to be a function. In this case, it just needs unit. So I submit something to the thread pool, and that something is just the run loop. And once the thread pool fires, it's just going to pass unit to that run loop, and the run loop is going to keep going. And that's it. So every time you do this, you're triggering a yield. So you're giving back control by going back to the thread pool, which is going to queue you up and decide what other IO needs to run. And that's it. Then start. So this is like the interface in Cat's Effect, where you basically have, you spawn an asynchronous IO, concurrent IO, and it returns this fiber thing. So but actually fiber is just a handle over a run loop. So fiber itself doesn't do anything. So IO themselves are already kind of fibery. They're already like that concept of like sequence of steps. A fiber is just a handle that lets you do a couple of things with it. You can call join, which is going to do semantic block for completion. And I don't have time to explain how he does it, but he uses a thing called deferred, and ultimately deferred uses ref, and at the end of the day, it ends up being async. So everything basically boils down to async. It's so key. And also, it allows you to cancel the fiber. So interruption is out of scope for this talk. I don't want it to last for 4 hours. But basically, it's just a way of saying to the run loop, OK, now stop iterating. So basically, interrupt whatever you're doing. But as it turns out, this raises a lot of questions about resource safety and what's the best interface for interruption. So we're just gonna skip it. But we can look at a simpler version of start, which is just the one that spawns a run loop, but without giving you a handle. So you're just going to start something asynchronously, but without any notion of joining or canceling. And it's the equivalent of doing start or void. So bear in mind that this is leaky, because now you're spawning something that you cannot cancel, but like all of these things are low level. So just use FS2 in practice and don't have to worry about any of this. So how does this work? So again, I'm going to just shift. I'm going to compose the IO I get passed in with shift. So remember that shift means submit to a thread pool. So what I'm doing, I'm going to submit something to the thread pool, and the first, and then the shift is going to pass the rest of the computation, which is a flat map, which ends up being this IO. So basically what I'm doing is I'm going to take the whole IO and put it on the thread pool. And therefore I'm generating this sort of asynchronous forking point there. And then this is like on its own, and now I just call back with write. So I don't wait for that IO to finish. So the difference is that I don't pass the callback inside here. That will make it kind of linked. I actually sort of sever that path, and that gives you this idea of forking without sort of synchronization. So this is a bit like dense. So come back and talk to me in private if you want to understand a bit more about this. And then sleep. It's quite similar. It semantically blocks for a given duration. And again, semantically blocking means just suspending. And in this case, I'm going to use the scheduled thread pool. Again, I'm going to use async. This callback means the rest of the I/O. So I'm going to schedule a function to this schedule executor service for a certain length. And that function, in turn, is going to schedule the rest of the I/O into the thread pool. So there's 2 hops here. I first go to the schedule pool where I sleep, and then from there I go to the actual pool when I resume. So you can see that this callback, it actually kind of reifies your I/O. Given that we passed the run loop, we're just taking that run loop and moving it wherever we want. And that's how we achieve that idea that I showed in the first pictures of moving something, in different logical threads. And then finally, should be on time, how to put it all together. I'm going to have this put method that just calls print line. And this periodic function, it's a simple loop. If I equals n, I'm just going to return unit. And if not, I'm going to run the action, sleep for a while, and then sort of recur. And then I'm going to use start to concurrently spawn 2 periodic computations. So what you're going to see 501 being interleaved with 502 at a certain sort of time cadence of 300 or 200 milliseconds. And I just want to take a second to sort of reason about how different this looks from the internals. So you have a very simple synchronous interface, but now you have some idea of all that's going on under the hood of things getting moved over back and forth under this beautiful sort of synchronous interface. And by the way, this is a version with FS2, which is better. First of all, it's higher level. See that you didn't have to merge all the concerns of time-based and stopping after 7 and repeating something. And also it's safer because it keeps track of interruption and it propagates it. So that if you interrupt one of the stream, the other also gets interrupted, you never leak resources. So it's safer, more composed on a higher level, but ultimately based on the same building blocks. So we have this huge tower of abstraction, which then ends up just being a bunch of callbacks getting called in thread pools. So, and it's both very lightweight, so performant because you have no blocking, and kind of beautifully simple, both in the abstraction itself and in how it gets translated. And you can imagine this like, for example, you can run over Node.js, and in fact you can run over Scala.js. Instead of dealing with callbacks manually, you build this synchronous interface, but at the end of the day, all asynchrony ends up being callbacks. So again, concurrency is about abstracting. It's not about how things are run. It's about how things look like in your code. How do you structure your code? So there's still things that we haven't talked about. We haven't talked about interruption, which is a huge topic. We haven't talked about resource safety. How do we ensure that resources get closed concurrently? We haven't talked about stack safety. We haven't talked about how to deal with actual thread blocking. So if there's an API that actually blocks, then you kind of get screwed because your thread is running many fibers, and then one call is blocking it, so you're taking a lot of fibers out. And so we have ways of moving that to a different pool, and it kind of complicates things a bit. If you can avoid using blocking APIs, all the better. But if you can't, we do have tools to help you deal with that. And then we haven't really talked about FS2's higher level API, and now we managed to achieve the higher compositionality and safety. But I just want to, again, go full circle and look at this very simple example of, concurrently waking up every second and sending things to sockets. And again, think about all that's going on under the hood to make this happen. And the only conclusion I can have for that is that abstraction is great. So this talk was like a journey into what you don't have to see. So the whole point of building this is that you now get something that is composable, that is performant, that is high level, and you don't have to see all the details that go into building it. So hope you enjoyed it. And these are my sort of links. My slides are going to be on my blog soonish. And I also have example code where I have a few interpreters of I/O, so I might enrich that over the next few weeks. And I'm not on Twitter, but I'm on GitHub, so reach at system@omega or just come talk to me after. And I think we're on time to take a big break before lunch, so thank you very much.